Okay, it's Berkeley time. Let's begin. Welcome to, can you guys hear me?
Yeah, I can hear you.
Okay, welcome to the Recommendation Systems decal. This is our first lecture, and we'll start off by introducing the core staff. I'm Andre, and Arvin can introduce.
So hey everyone, really great to see you here and excited to get this decal up and running. My name is Arvind and I'm a sophomore majoring in EECS and business. And yeah, I'm helping out with teaching the decal this semester on recommendation systems. Sid, do you want to go next?
Sure, yeah, I'm Sid. I am a sophomore majoring in ECS and business. I am just an education officer at MLab. I'll be in charge of some of the material for this course too.
Emmy, do you want to go next?
Oh, yes. Can you hear me?
Yeah.
Okay. Yes. Oh, hi, I'm Emmy. I'm a junior right now in CS, and I'm just in lab for this education decal and some research.
Yeah, and you also see there are 3 other instructors here who aren't here today, Max, Arjun, and Tage. So they help with more of the behind the scenes stuff. So they might not show up to lectures, but you may see them sometimes. Yeah. Okay, so now that we've introduced yourselves, we'd like for all of you guys to introduce yourselves as well. So I'll just go down the list alphabetically of who I see first. And then when I say your name, if you could just say your name, like major, year, and maybe a fun fact about yourself. So Ayush, we'll get started off with you.
Hi, my name is Ayush. I'm a freshman EECS major, and a fun fact is I love tennis.
Great. Abby?
Hi, everyone. I can't turn on my camera right now, but hi, I'm Abby. I'm a sophomore studying data science and statistics. And if I remember correctly, my fun fact is that I can speak Portuguese.
Very cool. Alessandro? Okay, no worries, Alessandro. If you want, you can introduce yourself in the chat and then everyone can see it. Alexander?
Hi, I'm Alexander and I'm an EECS major, a junior. And a fun fact about me is that I can speak English, Mandarin, and Cantonese.
Nice. Arnav?
Hi, I'm Arnav. I'm a CS major. I'm a senior. And the fun fact about me is that I enjoy playing golf.
Nice. Ilya?
Hi, my name is Ilya. I'm an EECS major minoring in data science. I'm a junior, and fun fact about me is that I can speak Farsi.
Nice. Giovanni?
Hi, everybody. I'm Giovanni. I'm an EECS major, and I'm a senior. And fun fact about me is I have a twin brother, and I can speak Norwegian fluently.
You guys all know a lot of languages. Henkai? Okay. If Henkai later on, if you you can also type your introduction in the chat if you can't use your mic. Huibo? Okay, yeah, Huibo's introduction is also in the chat. He's a CS and cognitive science double major, and he's a junior. Izzy?
Hello, I'm Izzy. I am a senior. I'm double majoring in Cog Sci and Comp Sci and minoring in data science. My fun fact is I'm an adventure junkie, so I've gone skydiving. And then I also got a tattoo without telling my mom.
Oh, very cool. Okay, Jason?
Hello, I'm Jason. I'm a CS major, and a fun fact about, I'm also a sophomore. A fun fact about me is that I like playing ping pong.
Nice. Jillian?
Hey guys, my name's Jillian. I'm an EECS major, and fun fact, I'm a sophomore, and then fun fact is I love to cook.
Johnny?
Hi, I'm Johnny. I'm also a geek sophomore, and a fun fact that it's also I love cooking.
Nice. Okay. Justin?
Hello, I'm Justin. I'm a junior, double major in CS and applied math. Fun fact about me, I feed a squirrel at home.
Nice. Okay. Kadon?
I am Kaden. I'm a senior studying statistics. I guess fun fact, I like going fishing, but I never catch anything.
Cool. Okay. Caitlin?
Hi, I'm Caitlin. I'm a fourth year CS major, and my fun fact is I can play the piano, ukulele, viola, and flute.
Nice. And I think Naman had, he introduced himself in the chat. He's a EECS major who's a sophomore, and he's also from Denver. So then now Nancy?
Hi, I'm Nancy. I'm a senior studying computer science, and my fun fact is I have a twin sister.
Cool. Peter?
Hi, I'm a second year studying computer science and economics. Fun fact about me is that I used to live in Fargo, North Dakota.
Nice. Philip? Oh, yeah, Philip also introduced himself in the chat. He's an exchange student from the University of Munich, very cool, and he's studying economics and statistics. Rhea?
Hi, my name is Rhea. I'm a freshman studying computer science, and a fun fact is that I do figure skating.
Nice. Rishi?
Hey, I'm Rishi. I'm a second year CS major, and fun fact about me is I love dancing.
Ooh, very cool. Ritwik?
Hi, I'm Ritwik. I'm a sophomore EECS major, and a fun fact about me is I've never broken a bone.
Nice. Royce?
Hi, I'm Royce. I'm a freshman studying CS, and a fun fact about me is I built my own PC.
Very cool. Rofeng? Rofeng also typed in the chat. He's a CS and econ double major who's a junior. Fun fact is that he can solve a 3x3 Rubik's Cube in 15 seconds. Yeah. Sanskar?
Hey everyone, I'm Sunskar. I'm a second year EECS major, and I guess a fun fact about me is that I spent 3 years of my life in Sweden.
Nice. Sebastian?
What's up, guys? I'm Sebastian. I'm a fourth year cognitive science major and minoring in data science. And a fun fact about me is that I produce music.
Very cool. Charville? Oh yeah, Charville. He's a EECS major who's a sophomore, and a fun fact is that he likes to play chess. Shigia?
Hi, I'm Bronya. I'm a junior and majoring CS. And one fun fact about me is that I have to eat and going to this class at the same time.
Nice. Srinath?
Hey everyone, my name is Srinath. I'm a CS major, sophomore, and fun fact about me is that I'm from New Hampshire.
Nice. Tianlun?
Hi, you can just call me TL. I'm an EECS senior, and the fun fact will be I can sleep 20 hours a day.
Nice. I need 20 hours of sleep too. Varun?
Hi everyone, I'm an EECS senior. Fun fact is that I'm also a music minor. I'm in 2 ensembles on campus, and I play like 4 instruments.
Cool. Jenny?
Hello, everyone. I'm a first-year master student from the School of Information. Fun fact of me is I went cliff jumping in Utah this summer, which is very funny.
Nice. Wute?
Hi, I'm Ute. I'm a junior in Inks, and a fun fact is that I used to live in New Zealand for 2 years.
Cool. And lastly, Yizhao?
Oh, hi, I'm Yujo. I'm a third year major in computer science and comp sci. Fun fact about me is I like cats.
Nice. Okay, I think that's everyone. Is there anyone who didn't introduce themselves? Okay, looks like everyone introduced themselves, so we can go ahead. So yeah, basically this is the first lecture for recommendation systems. And each week, you notice that there are 4 instructors here today, so we'll all be each teaching different weeks. So Andre is going to be mainly teaching the lecture today. And yeah, Andre, you can go ahead.
Let's start with talking about the course policies. So our lectures for now will be planned to be online on Zoom, but there is a possibility that we will find a room for this later, if that is what the students want. So for the homework, we will prioritize understanding of concepts. We won't grade them based on model performance. Like we won't grade them based on your model's accuracy. We'll mostly our main metric is whether or not your model demonstrates an understanding of the technique that we're teaching. So each week we have an 80-minute in-person, we have 80 minutes of lecture at this time until 7. And then after the lectures, there'll be 50 minutes of office hours. Although we realize that not everybody, not people probably won't start the assignment directly after the lecture. So we might move the office hours to a later time so that you guys can get started on assignments before coming to office hours. And for the policies, yeah, the grading scheme is that 40% is homework, 30% is quizzes, and 30% is participation. So to pass, you'll need 70%. This class is PNP, like all details. Yeah, actually we changed how we haven't updated the slides after we decided on how we're gonna hand out assignments. For assignments, you'll be working with Google Collab notebooks. So we'll share them with you, and you'll be able to copy them over to Google Drive. And after you run the notebooks and get the results, we'll just ask you for a PDF of your notebook along with your code and their outputs. Estimated time is 3 hours per assignment per week, and you get 2 free homework drops. The quizzes take 30%. So every week we'll have open book multiple choice forms based on lecture content. And these are graded based on percent correctness. The estimated time is just 10 minutes per week. And they're graded on a curve. So you'll get full score if you get 9% basically. Participation is the remaining 30%. So that means coming to online lectures, then participating in class in the forms of maybe asking questions. And this is just 80 minutes per week. It's just the lecture time. For communications, we'll be mainly using Piazza, and the person who's giving the lecture that week, which is me for this week, will be the one who's mainly responding to questions on Piazza. Then you can also email our class email for other questions, and it'll follow the same pattern. The person who's running that week will be replying more often. Yeah, and then as we said, after lecture, there's 15 minutes of office hours. You can come here for questions. Now, what is this course about? Well, we're obviously gonna teach recommendation systems, right? But we don't want this class to be just like an application class where you learn to only use the models. Of course, like application will be important. We want you to understand the advantages and disadvantages of all sorts of recommendation systems and know how to make decisions based on specific application scenarios. But we also want you to understand the theory behind some of these models, so that you might be able to tune them or make the right adjustments depending on specific use cases. Yeah, we'll go over many types of recommendation systems in this class, and we'll try to focus on some on the ideas of like we'll focus on both like the theory behind them and also like when you should use a specific type and when you should avoid using that type of recommendation system. Okay, so what are recommendation systems? Well, it is pretty much what the name suggests. They're algorithms that aim to suggest relevant items to users. And so, you know, a lot of these common recommendation systems like YouTube, Facebook, they recommend different sorts of items, like YouTube recommends videos, Amazon recommends stuff to buy, TikTok, Spotify recommends music, and they all use different information to make these recommendations. But in general, recommendation systems are just systems that recommend certain items to users, and they can vary a lot based on what information they use to make these decisions. And they all have a common goal to keep increase utility for users. That means finding items that are useful to users, or they try to keep users engaged on the platform. So that might manifest in longer watch times and longer time spent on these platforms. So to give a brief history of the early recommendation systems, these are what we usually call classical methods. So they don't involve like deep learning yet, but they'll give you an overview or like give you a rough idea of what sorts of attempts we have made towards building recommendation systems. So the earliest one is Grundy. It's a book recommendation system. What it does is it interviews users to get their preferences, and it basically puts users into groups based on categories of books they like, and the system just recommends books from that category to that user group. And then there's this tapestry system that starts to use collaborative information in making recommendations. The collaborative means that an item might be described by not just the content in itself, but the system will also consider other users who have interacted with the item in order to decide who this item should be recommended to. So in this case, they'll have users collaboratively comment on these documents. So they'll make comments and labels on the documents, and the system is able to use these annotations to determine the category of the document and therefore which users to recommend it to. Salton is the first recommendation system that starts to use vectorized representations for items. We'll talk about this later, but vectorized representations is like a very flexible, very general way of representing multi-dimensional information, right? So for one item on Amazon, for like a chair, you'll have different numbers that's represented. You cannot represent it really with one discrete variable. So the most flexible way of representing information about this item is using quantities that describe separate dimensions of it. So that could mean physical dimensions, like its actual length and height, or its price, or like how much it has been used, and other quantifiable information like that. And then finally, Netflix has the sign match algorithm that came out of a competition where competitors were asked to build like the best performing recommendation systems on a certain benchmark data set. And eventually they built a hybrid model that combined 170 channel algorithms to get its performance. And it was a pretty successful model just from Netflix. So now we'll start talking about the types of recommendation systems. So the first, and I believe personally the most simple one, is content-based recommendation. So it's basically recommends items that are similar to what a user looked at in the past. So this works well when the user preferences largely determine what items they'll buy. So like food shopping, and when you're making customized searches, when the user has a relatively fixed set of preferences, and that's and where they usually look for the same type of items. Now, this will often use some sort of similarity measure between items because you need to have a way of evaluating how similar two items are to determine whether one should be recommended to the user that viewed the other. And later on, we'll see that vectorized representations, as used by the Salton system, is a convenient representation that allows these similarity measures to be computed. Now, yeah, so vectorized representation, a vector is basically just a list of numbers. You might have seen it in physics as an arrow with a magnitude or direction, but really it is just a multidimensional set of numbers. These numbers could represent all kinds of things. They can represent different features of the item. Yeah, and so obviously each entry can describe a quantitative feature, but when we have qualitative features that are discrete, we can also break that down into multiple binary features. So for example, if you're trying to represent whether an item is used or new, you can have one entry that is just 0 when it's new and 1 when it's used. It doesn't necessarily have to be a quantifiable feature. Qualitative features can be represented this way as well. Now, most of you probably have seen the dot product. The dot product is computed between two different vectors. Okay. So the way you compute this is you take the sum, but you take the sum of the entry-wise products. So you'll multiply the first entry in vector v by the first entry in vector u. You add that to the second entry of vector v multiplied by the second entry in vector u. So this way, you'll get this sum, which is a scalar, not a vector. And there's an interesting property where the dot product between a vector v and u is equal to the magnitude of v. So this magnitude is what you probably see in physics. When you understand the vector as an arrow, this magnitude just represents the length of the arrow. So the interesting property is that the dot product between these two vectors is equal to the product of their magnitudes multiplied by this cosine theta, where theta is the angle between the vectors when you represent them as arrows in space. Now this is useful because this cosine theta term, it almost automatically gives us a way of measuring the alignment between these two vectors. And we don't have to really do any complicated computations. We're just multiplying terms and taking the sum of all the products. And intuitively, you can sort of see why the dot product is a measure of similarity. If you have two large terms that are both positive in an entry, you'll get a large product. And so when that's added to your dot product, you'll get a large dot product. Well, if you have a mismatch, so if on some entry your first vector has a large value while the other vector has a large negative value, then that will contribute a very negative term to the dot product and therefore decrease it. So one example of how you use dot products for a very basic content-based recommendation system is where you say you have a list of apps, right? Which are represented by their icons on the left. And each of them, you can label whether it belongs to a certain category. So the first app, it is an education app. So you'll put a 1 at the entry that corresponds to the category of education. And it's also a science app, so you'll put a 1 on the entry that corresponds to that category. And the rest of the entries are put to 0 because this app doesn't belong there. And similarly for the second and third items, you basically use 1s to mark the entries that represent a category that this app belongs to. Now, a user would have a history of items that they looked at, right? So we can collect all the apps that they looked at and look at the vectors. So one thing we can do is take a sum of all the vectors that represented the items that this user has interacted with, and then take the dot product between that summed vector and say a random app that we would like to decide whether or not to recommend to the user. And if that product is large, we know that this new item we're considering is very similar to the items that the user has interacted with in the user has interacted with in the past, and we can recommend it. And if it's a small dot product or a very negative dot product, we would try to avoid recommending it. And then the second type of recommendation system is collaborative filtering. This is a bit more advanced than content-based recommendation systems, in my opinion, because now you're using collaborative information. So the idea behind this type of system is that it assumes if person A and B had similar tastes in the past, then B's preferences could predict what A prefers in the future. So in a way, you're grouping users into similar groups, but you don't have to explicitly group them. You can also use a metric like the dot product we've seen before to measure the similarity between users, and therefore use that to influence how much like users A preference should influence your recommendations for user B. Yeah, there are different ways to do this. One way is to explicitly have the users label items, like the tapestry system, where users are asked to annotate documents, or you can use implicit connections. So say on Amazon, you don't exactly need to ask the user to annotate the item they buy, but if say user A buys items, but buys a certain category of items together, then your system can begin to infer from that information that that set of items is similar, and use that to influence its recommendations to other users. One example is matrix factorization. This might look a bit daunting at first, but so imagine the case where you have vectors that represent users, and you have vectors that represent items. So suppose you already know these vectors. You know that, suppose you already know these vectors, and the dot product between a user vector and an item vector represents how similar the user's preferences are to the item's features. So what that means is a user will we're saying that a user will like an item if the dot product between the user vector and the item vector is large, and they won't like it otherwise. Now, if we stack the user vectors like this into a matrix and also stack the item vectors into a matrix, we realize that the matrix multiplication between these two matrices basically takes all the possible dot products between user item pairs and puts them into the entry of this resulting matrix. So the entry at row B and column W over here will correspond to the dot product between user B's features, between user B's vector and item W's vector. So we can understand this as a rating matrix because it's sort of predicts how much a user might like this item. Now, in practice, you won't have the user and item vectors to begin with, but you'll have this rating matrix from the history of interactions on your system, right? Users, you can determine these ratings in all kinds of ways. They can be explicit ratings by the users for the items, or you can just infer from the fact that the user chose to interact with an item. You can infer that fact that that the user would give a high rating to that item. So this might also be binary, but the idea is you'll begin with this rating matrix and try to factor it into a user matrix and item matrix. Now, there are multiple ways to do this. If you have a matrix that isn't super large, those of you familiar with linear algebra, I realize that you can use singular value decomposition to do that. And if you have a very large matrix where singular value decomposition isn't necessarily feasible, we can use gradient descent methods to do that. But right now, we won't go too deeply into how to actually solve it. But I think just looking at this sort of tells you what you're solving for, right? You're looking for the user representations and the item representations, which produce the rating matrix that you observe. later we'll come back to the specific ways to solve this factorization. The last type of recommendation system is knowledge-based recommendation systems. This is when only using the user's interaction history alone can't produce good enough recommendations. Now, you can imagine, so like a website that sells cars or rents apartments wouldn't have a lot of interaction history from specific users. It also just wouldn't have a lot of interaction history overall because interactions are very sparse. The user probably only buys a car or rents an apartment every few years. So you won't get very far by just looking at what they did in the past. In this case, it's better to actually query the user and ask what they want. So some of these systems might just have the user input, what's the price range of the apartment they're willing to rent, what's the location, and then use these queried preferences to make recommendation systems. Now, this would require domain-specific knowledge, so the system would need some way of using information about the domain that is making recommendations. So for example, it would need to know models of cars. It would need to know what models of cars fall into a certain price range. It would need to know it would need to know all kinds of information about the items and have some sort of categorization so that these current preferences are actually effective. Okay, so a recap, we talked about three main types of recommendation systems. So content-based systems, they just, the basic idea is you recommend items to a user that are similar to what that user used in the past. And the collaborative systems rely on the idea that people who agreed in the past are likely to agree in the future. So you can use a similar user's interaction history to predict the future preferences of another user. And the knowledge-based relies more on domain knowledge and queried information from the user to retrieve items that match specific needs expressed by the user. And of course, in practice, models aren't strictly collaborative or content-based or knowledge-based. They're often hybrid. And probably for the system we'll see later, sometimes there isn't even a clear classification of which category it belongs to. Okay. Not sure how to do a poll, but so consider this example where you're an engineer at Coinbase. You're developing a recommendation system for users that will recommend cryptocurrencies based on certain factors like the user's risks appetite, when they want to retire, their preferred industries, domains, applications, and coins they have had success in the past. So what type of recommendations, what type of system do you think will work well in this case? You can just type your answers in the chat. Yeah, I would also say knowledge-based is maybe the first system you should try, because just from the way this is described, a lot of these are specific information input by the user, like when they want to retire. And also a collaborative system, a hybrid between collaborative and knowledge-based system could also work because as it says in the last part, we can also make use of information about which coins they had success in the past. Yeah. Now we'll start talking about various problems that recommendation systems face. And actually, these are the problems that the systems we'll see later on in the course are aiming to address. So the first problem would be serendipity. What this means is, like, imagine if you had a very naive content-based system that simply recommends items that are similar to what a user used in the past. This is very likely to get caught in this trap where the user only views, where they might get caught into this trap where, so you start by recommending a item similar to something the user likes. And then your recommendations will make it so that the user is more likely to choose that sort of item because they just see more of it in their recommendations. And from that, you'll start drawing the false conclusion that the user actually likes that. You'll start to overestimate how much the user actually prefers that sort of item because your recommendations are making it more likely for them to pick it, even though they might not prefer the specific category as much as you estimate. Now, like an example is, I think YouTube feels sort of problematic in this way. It's very sensitive to what videos you watch. So maybe your friend sent you a link of a cat video. After you watch it, your recommendations are most likely going to be flooded with similar videos. And then if you're not careful and click another one, it's most likely it'll take a while before you get out of this whole cat video thing. Yeah. So the potential solutions are, one is to look at how similar users have shifted interest in the past. This is collaborative in nature because you're looking at other similar users for predictions of this user's preferences. And you can also use domain knowledge if the domain has any if the domain has useful heuristics. So you might know that if a user prefers items X, they're more likely to need Y in the future. So this might work when, say like your user buys a notepad. Then you can guess from domain knowledge that they probably also need a pen instead of recommending more notepads. Yeah. Another problem is cold start. So far, a lot of the systems we described rely on the fact that you have user interaction from the past, but a new user doesn't have any informative history with your system. So one problem is determining how to keep this user engaged. Like if you can't give the user recommendations that they like in the beginning, they're very likely to just leave your platform, right? So one way to get around this is just to query the user for more information. A lot of the apps nowadays do this. So like when I sign up for Twitter, something like that, it asks me for like which type of news I would like to look at. Like I can pick technology, gaming, whatever. Yeah, so that's one way to get around cold start. And all different apps have different ways of doing this. Some just import contacts, like Facebook looks at your contacts and then just recommends those people as your friends. And yeah, generally they're all ways of just getting more information. And because there's really not much you can do for a user that you don't know anything about. Of course, like if you have an AE system, you can always like take the average of all users to represent a new user, but that's might not work too well in practice. And also a problem is feature abstraction, because it's not always easy to describe an item in a quantifiable way. So so far for the systems, we're assuming that we're going to manually pick out the features. At least for the content-based systems, we're assuming that we'll manually label the items for what features they have. Now, this is not always feasible when we have too many items. Also, sometimes it's not clear which features are important. You might imagine the dot product example we mentioned earlier. In that case, like whether or not an app is a social media app or whether the app is a education app are considered equally important by the dot product metric. So in that case, it's actually harmful to pick more features that aren't as relevant. And we don't have a good way of weighing which features should dominate the similarity measurement. Now, later on, we'll talk about more complex ways of actually labeling these features. One way we actually already saw is collaborative filtering. We're just using user history to label an item instead of manually labeling of the item by its features. And for more complicated forms of input, like natural language, like if we have a text paragraph that describes the item, we'll still want to quantify that into some form of vector so that we can actually compute similarity methods, right? And for that, we might use methods like natural language processing, and neural methods often work well for these problems because they can capture these nonlinear, very high dimensional relationships between the input and the features that you want to produce. Now, there are many more problems that have to do with the scale of your recommendation system. So for the dot product example we talked about before, also I guess for the matrix factorization example, they require us to compute a lot of pairwise dot products, and this can scale very poorly when you have a large user base because it scales quadratic, right? You need to consider every pair of user and item, and that is like your system may not be able to catch up to the number of incoming users. And we also have problems with processing large data sets having sparse ratings, which means that a lot of items in your systems might not have been rated, so they don't really have much interaction history. This is especially true for online recommendation systems because, like, for the classical ones we talked about, like the book recommendation system, most books have been read by some people, and people are pretty clear about which category of books they prefer. But on the internet, the vast majority of videos, like the tail end of the distribution, has not had many views, and the system has to find a way to recommend new content that hasn't been watched to users. Otherwise, it will just keep recommending the old videos that have a lot of views and never get anything fresh on the platform. Yeah. Are there any questions? I think someone asked something about the dot product in the matrix factorization slide. Okay, why the dot product was between B and W and not A and W? Oh, like I was referring to the entries here. It's row B and column W, this 4.0. That would be the dot product between the second row of the user matrix, which is user B, and the first column of the item matrix, which is item W. Yeah. Are there any questions? You can type it in the chat. If not, I can start talking about the homework. Okay, so this week's assignment will be mostly introducing you to NumPy and Pandas. These two are libraries in Python that are very useful for processing data. So NumPy is mostly useful for processing like matrices and vectors, while Pandas will be better for data that's formatted like Excel, right? CSV files that have maybe non-quantitative information. Then Pandas will work better for these sorts of data than NumPy. And we might also use them together to work with data. And in the end, we'll show you an example recommendation system that uses Pandas, but you won't have to implement this. Your job will be to answer our questions about NumPy and Pandas. So we'll ask you to say to like, given a matrix, write a function that takes every fifth row of the matrix, and then you'll write some sort of function in NumPy. That will be the sort of questions we have in the assignment. And the way the assignment will be given is it'll be in a Google Collab notebook. If you have used Jupyter notebooks in the past, this is basically the same thing, but it's online. Now, if you haven't used Jupyter notebooks, think of this as a Python interpreter that allows you to run code in cells and also remember what each cell is. So if you're working in just a Python interpreter in the command line, you might like type a chunk of code and then realize you want to change something about it and then run it again. But if you're just in an interpreter, you would have to copy it from, you have to scroll up, copy it, and then paste it into the command line. And that's quite inconvenient, right? Because it would be convenient if there was a way to memorize chunks of code and the order in which you wanted to run them. And that is exactly what Google Colab is for. So one thing to clarify is that, like, if you have, like over here in the image, you have two cells, the first code cell and the second code cell. This doesn't necessarily mean that when you run the notebook, the second one will always be run after the first. Like you can repeatedly run the same cell, or you can run the first one, run the second one, and then come back to running the first one. Running it is equivalent to inputting the code in that cell into a Python interpreter. Everything is interactive. So yeah, just think of it as putting that chunk of code into a Python interpreter. One thing that might cause some problems is, unlike a Jupyter notebook that can directly access files in that folder, Google Colab, to access other files on Google Colab, you'll have to mount it on your Google Drive. And we have instructions in the notebook for how to do this. But to get started, we'll post a link later. That's the folder containing the weekly assignments. You'll copy that. You won't be able to edit that directly, but you can copy it to your own drive, and then that will be the folder where you do the assignments. Yeah. Yeah. And for Google Colab, there's a toolbar on top that has most of the utility you'll need. So for a Python interpreter, there's a way to exit, right? There's a way to like basically restart the interpreter, and that way you sort of reset your memory. You erase all the variables that you memorized. So in Google Colab, the runtime tab has these functions. Like you can interrupt your execution. This is more or less equivalent to just pressing Control-C in your Python interpreter. You can restart your runtime. This basically just resets the runtime, which includes all the variables. And yeah, if your Colab notebook runs into problems runs into very obscure problems, you can always factory reset it, which puts it back into like an unedited form. Yeah, and one little thing about Google Colab notebooks is that in Python interpreter, when you evaluate something, but if you don't print it, it doesn't. Wait, actually, it does in a Python interpreter, but in Google Colab, the first results that you evaluate but don't assign to anything in each cell will be automatically printed at the end of the cell. So here, you didn't really ask it to print numpy a range, right? But because you didn't assign this to anything, it will automatically print it.
Okay.
Any questions about the assignment? Of course, like feel free to ask questions once you get started, but any questions so far?
So Ilya, basically the homeworks will usually be due by the start of lecture. So by next week's by 5:30 p.m. And we'll be posting the homework on the course website shortly. Watch out for an announcement on Piazza. So once that announcement is posted on Piazza, which you should get an email for, then the assignment, the slides, the lecture recording, everything should be up by then. And yeah, Naman, there is a course website. So let me send that in the chat. Yeah, and if just before you guys leave, just a few things to note, just to make sure that you guys are like that you guys have access to everything. Make sure that you have access to Piazza and the Gradescope. Piazza is where like we'll be sending all of like the emails for when stuff is due, and Gradescope is where you'll be submitting the assignments, like a PDF version of them. And if you like, you should also check your guys' spam folders. If you guys got an email from rexis.fa21@gmail.com, try to unmark it as spam so that like in the future, if we send emails, it doesn't automatically go to spam. Yeah, and just a few other things, just like throughout lecture, if you guys ever have questions, then you can just raise your hand through the Zoom feature, or you can ask questions at throughout the lecture. It doesn't even have to be at the end. And yeah, that's basically it. Sebastian, so will the first quiz be on these slides and also do next Wednesday at class? Yeah, so the quiz will usually be the content on the week before, and the quiz is very easy. Like it's going to be like multiple choice. It's not going to like, we're not going to try to trick you, and it'll be due by the end of day Wednesday, because we know that there's some people who have like scheduling conflicts and stuff, so they may not be able to finish it during lecture. So it'll be due like at the end of the day for that on the lecture day. And Charville, OH office hours hasn't been decided yet for this week. So in that Piazza announcement, we will be posting when we'll have office hours for the rest of the semester. Yeah. Also, one other thing is we were potentially thinking of opening the decal in person as well. So right now we have it on Zoom, and we'd still allow people to continue using it on Zoom. But if there are some people who would prefer having an in-person option as well, we could also rent out a room in like maybe like Brunel or something like that, and the people in person can come. Like there could also be people coming in person. So we'll send out a poll maybe on Piazza as well through the first week announcement about whether you guys would prefer to have in-person or Zoom lecture. Elia, is the quiz on Gradescope? Yes, not as of now, but we will be posting it on Gradescope. And Justin, do we have readings or notes if you'd like to delve a bit more info into the content? So yes, actually this week we didn't have too many, usually we'll have research papers with each week's slides, but this week we didn't because obviously it's the intro lecture, and we just wanted to spend more time going over like the background of recommendation systems. But once we start going into like the technical topics, we'll be like having papers, and it would be great if you guys could like read those papers before lecture, since during lecture we'll go over them and then you can like understand it better. Yeah, and yeah, if you feel free if you guys need to go. So we'll be usually lecture will end at 7, and usually it'll be like ending at 7 because we'll have a lot of content to cover. But since this is the first week, we'll be ending early. Yeah, thank you for registering the decal.